many other useful properties of Fourier transforms that we have discussed in the previous two videos. We have Parseval's relation, okay, and this the statement of the relation is that if xt and x omega, j omega, are the Fourier transform pairs, then the energy is conserved in both time domain and frequency domain. That is, if you have a signal, okay, that represents any physical quantity, it is volts or amps or whatever it is, then this quantity is the energy per unit time. Okay, it's the magnitude squared of that signal, and integrating this throughout the time gives the energy. Okay, this is the energy contained in the signal xt. This energy is conserved in both time and frequency domains. So either you can evaluate the energy in the time domain, or you can use the Fourier transform pair of xt, that is xt omega, and evaluate the energy in the frequency domain. Okay, so for example, this represents uh, the energy density per unit frequency. So this expression, magnitude of xj omega, magnitude squared, is also known as the energy density spectrum, and it is per unit frequency. So if you integrate this with respect to frequency over the entire frequencies minus infinity to plus infinity divided by 2 pi, it gives you the same energy, same result, same energy as that evaluated in the time domain. Okay, so this expression is referred to as Parseval's relation, and it follows from the direct application of the Fourier transform. So specifically to show this, you see this magnitude squared form of xt can be expressed as xt magnitude xt then x conjugate of t. So in general, x of t could be a complex signal. Okay. Then what you can do is you can bring the definition of inverse Fourier transforms. So in terms of the Fourier synthesis equation, this is the inverse transform of x star t. Okay, so you can bring the steric, the conjugation operation inside the integration. So the integrand is conjugated. So instead of plus, there is minus e j omega t, and there is steric over x j omega as well. Now you notice that so this whole bracketed thing is your x star t, right? This is x star t. So this is synthesizing x star t, not xt. So this is x star t. Now this integration is over omega, okay, and our initial previous integral is over the time, right? So xt is dt. So these two integrals are independent, therefore the order of operations, integration operations, can be interchanged. So if we interchange the orders of integration over omega and t, what we get is, so you can bring this x star of j omega first over here, right? You can write this as such. You can bring this multiplying factor 1 over 2 pi with it, and then you can bring xt forward, okay, inside, and then you can have this with dt. So d omega is there. So this bracketed term becomes this is inherently the Fourier transform of xt, which is xj omega. Okay, so if you combine xj omega with x star j omega, this becomes the magnitude squared spectrum, and that's per unit frequency. So if you integrate this with respect to frequency or the entire frequency range, well, that's energy. Okay, and that corresponds to the energy of the signal in the time domain as well. Okay, I mean, the intuition is that xt can represent any, for example, if it is representing the voltage of an electrical system. Okay, it's a signal that is representing, let's say it's a signal that is representing the voltage. For example, the capacitor is discharging over a load. So for example, the amplitude is in volts. Okay, so it becomes volt squares. Okay, volt squares, and if the load is normalized to unit ohms, it's volts per it's v square over r. So v square over 1 ohm is the power. So if the power is integrated with respect to time, it becomes energy. Okay, so similarly over here you have this expression gives you the energy density spectrum, that is energy per unit, not per unit time, but per unit frequency. That has to be integrated with respect to the frequency or all frequencies to give you the energy in the frequency domain. So the bracketed term is simply, okay, the Fourier transform of xt. Basically, this is referring to this bracketed term. So, okay, so this bracketed term is already xj omega multiplied by x star of j omega. Xj omega is usually a complex quantity. This becomes xj omega magnitude squared. Okay, so this is what it is. So the term on the left hand side of the above equation is the total energy in the signal xt. So Parseval relation says that this total energy may be determined by either computing the energy per unit time, that is represented by magnitude of xt squared, and then integrating over all the time, or by computing the energy per unit frequency, so and then integrating over all frequencies. So these two operations are the same, they are equal. Okay, the result is the same. So for this reason, magnitude of xj omega magnitude squared is often referred to as the energy density spectrum of the signal. That represents the energy density per unit frequency of the signal xt. So note that the Parseval relation for finite energy signals is the direct counterpart of Parseval relation for periodic signals, which, if you recall, were expressed in terms of Fourier series. So which states that the average power of a periodic signal equals the sum of the average powers of individual harmonic components, which in turn are equal to the squared magnitude of the Fourier series coefficient. So if you recall, fxt is a periodic signal, then we said that okay, this can be expanded in terms of Fourier series expansion. That is, you have Fourier series coefficients, AKs, and then you have harmonically related exponentials. So this is the expression is like this: jk omega naught t. So for this case, okay, omega naught is the fundamental frequency of xt. So if you evaluate the power of xt over one period, okay, so it's like this: magnitude squared dt. Okay, since it's the power, so you have to take the average over one period. So this integration has to be carried out over one period divided by the time period gives you the average. So this is the power. Okay, this is the energy. Taking the average over one period becomes the power. Okay, it's the power in one period, and this can be related to the Fourier coefficients. So that the intuition is that the Fourier coefficients, they represent the amount of power each harmonic is contributing. So magnitude squared of that, either you can do this evaluate the power by taking the magnitude squared of the harmonic components amplitudes discretely, or you can take the you can sum this up. Okay, k in general can vary from minus infinity to plus infinity. And this should be equal to the average power of the signal in the time domain. Okay, so I mean the Parseval relation for the Fourier transform representation of xt, where xt could be either aperiodic or periodic, it has a very similar. I mean, the analogy is the same as you had it for the Fourier series energy conservation in both time and Fourier domains. Okay, okay. So the Parseval relation and other Fourier transform properties are often useful in determining some time domain characteristics of signal directly from the Fourier transform. So let's take the next examples for illustration of this. So I mean, the idea behind discussing all these properties is to ease our analysis. I mean, there could be some pathological signals which are quite unorthodox, and to start with the direct Fourier analysis might not be very good idea. I mean, the mathematics involved could be very demanding over there. So what you do is you use these properties to ease the Fourier analysis. Okay, as an example, let's this is from the course text. Okay, 414, course chapter, and what it says is that you have to compute two quantities. Okay, so what we are going to do is we are going to use the Parseval relation. So we are not going to compute the magnitude squared of xt in time domain. We are not going to evaluate the power and then the energy, okay, of the signal in time domain. Instead, what we are going to argue is that since the energy is conserved in both the domains according to the Parseval relation, so this capital E should be equal to 1 over 2 pi x of j omega. That's the energy density spectrum if you take the magnitude squared. So this is also the magnitude squared spectrum of the signal per frequency. So it has to multiply by d omega in general minus infinity plus infinity. So these two expressions are equivalent. We know that. So usually xj omega could be as such that the Fourier transform, I mean, evaluating the energy in the transform domain could be much simpler. Similarly, if you recall, if you have to evaluate another quantity, so you see this example, what it asks for is that for each of the Fourier transforms, which is shown in figure 418, this is 418, and these are the Fourier transforms considered in example 414, we wish to evaluate the following time domain expression. So for this, capital E is representing the energy, okay, which is conserved in both time and frequency domain. This is Parseval's relation, and then D is the first differential of the signal xt. And if you recall, and this differential is being taken at t equal to 0. And if you recall, what does it means in the transform domain is that it's simply, and the Fourier pair is the multiplication of the transform of xt, that is j omega times x of j omega. Okay, and since you have to take the differential at t equal to 0, if you recall, what is the Fourier transform at t? How do you take the Fourier transform at t equal to 0? Well, that is equal to, I mean, by definition, this is xt dt. That's it. Okay, there is no, I'm not going to write e minus j omega t. Why? Because t is 0. Okay, so this is like minus j omega into 0 dt, right? So this quantity exponential is simply equal to 1. Okay, so don't worry about that. So it's minus infinity plus infinity. It's just like taking the area under the entire signal xt, okay, as a function of time. So that's the evaluation of the Fourier transform at t equal to 0. Then if you have to take the derivative, you have to multiply this with j omega. Okay, so let's start with the first expression. So we are given there are two transforms, okay, x j omega in figure A and figure B. So for the first figure, if we use, I mean, we don't need to evaluate the, so see, the thing is, we don't need to take the inverse Fourier transform, find xt, then takes its magnitude spectrum. Well, that's quite tedious. Okay, a simple way is to consider the transform itself and then evaluate the energy using the expression of Parseval's relation. So if you take the magnitude spectrum over here, you have to take the areas of the three rectangles. Okay, that's the first rectangle, then you have the second rectangle, then you have the third rectangle over here. So magnitude squared spectrum is easy to take in the frequency domain. So what you have for the first is this is under root pi. So okay, let's try to write the magnitude squared spectrum. So what we can do is we can have this. This is d omega. So we'll have three integrations from -1 to, let's say, -0.5, and then the same expression plus from -0.5 to +0.5 of the energy density spectrum. So we're going to have the same energy density spectrum in this range. Because this is constant in this range. I mean, in all these three ranges, magnitude spectrum is constant. Okay, so it's very easy to just use this directly. And the third rectangle is from 0.5 to 1. Okay, so these are three integrals that need to be evaluated to find the energy contained in the signal. Okay, all right, this is j omega. So magnitude squared d omega. So let's see if we can find this out. Well, magnitude squared energy density spectrum from -1 to 0.5 is pi. Okay, so this is simply pi, and then from -0.5 to 0.5, this is expression will be pi by 4. Okay, this will be pi by 4, and then for the third rectangle, this will be equal to pi. Okay, the first and the third rectangles are very similar. Then you need to integrate this, so let's sum this up. The integration is from -0.5 to 0.5, so this becomes pi, so omega -0.5 plus 1, so this is pi by 2 basically, pi by 2. And then we have plus pi by 4 multiplied by 0.5 minus 0.5 is 1, 0.5 minus -0.5 is 1 basically. So you're going to have omega over here, then 0.5 minus -0.5 is 1. And then for this region, the third region, the magnitude squared spectrum is the same as the first region. So this is pi by 2. Okay, this will be pi by 2. Pi by 2. Okay, let's see if we have done this correctly. So pi, yeah, it seems okay. Okay, this is well, this is E, right? And what we are missing is 1 over 2 pi. Okay, that is outside of these integrals. So basically, this we have to include 1 over 2 pi in all these three integrations to have the exact relationship of the energy in time and frequency. Okay, so what we can do is we can add this expression and then multiply by 1 over 2 pi to find what E is for figure A. And if you see this, this is pi, so this is 5 by 4 pi. Inside the brackets, the result is 5 pi by 4, and then you have to multiply this with 1 over 2 pi, and the overall result, the energy that is contained in the signal, which is also equal to, okay, the magnitude squared x of t, magnitude squared dt over all the time is equal to, pi cancels, and this is 5 by 8. This comes out to 5 by 8. Okay. So, okay, this means that this is a finite energy signal, which is quite evident from the spectrum as well. So, so for the second part, you want to do the same thing. There are two regions basically. So in the first region, the magnitude squared spectrum is what? It's j squared pi. Okay, and in the second spectrum, it's again plus j squared pi. Basically, you can just forget about j over here. It's pi. Sorry, it will be pi plus pi, and I mean the area will be the same. The magnitude squared spectrum. I mean, if you take the magnitude squared spectrum, then it's just a rectangle. So this is pi. Magnitude is under root pi. So magnitude squared is pi. Okay, and this also basically reverses its direction, and the rectangle will be like this, and this is pi. So it becomes 2 pi. And so this is the energy density spectrum for figure B, magnitude squared pi. Oh, sorry, it's like this. So this is 2 pi, but that has to be divided by 2 pi as well. So to find energy, you have to integrate this both sides, and then divided by 1 over 2 pi. So I guess you have to divide this by 2 pi, and this should be equal to 1. Let's check if you have done this correctly. So to evaluate E in the frequency domain, we may use Parseval relation. That is, we can use the energy in the transform domain, instead of evaluating the inverse Fourier transforms and then evaluating the energy per unit time, magnitude squared of signal xt, and then integrating it over all time. So in figure 4.18, the energy is 5 by 8. Okay, so I think we have done this correctly. This result is okay for part A. For part B, however, you see this is pi, and this is overall rectangle of pi from -1 to 1. So the area is 2 pi, right? The area is 2 pi. Then we have to divide this by 2 pi to get 1. So this is 1 for 4.1 at P. So I think we are okay. So you see the utility of evaluating the energy, through Parseval's relation is quite useful. I mean, you don't have to evaluate the inverse Fourier transform. You can do the energy evaluation in the transform domain directly. Okay, just as we have done for the Fourier series. I mean, the power can be evaluated by considering the Fourier coefficients only. Okay, and I mean, intuitively, these things are quite evident, quite obvious in the analysis. So you don't have to evaluate the energy or the power considering the signal function itself. You can use the Fourier coefficients or the Fourier series representations, okay, and evaluate the energy in the transform domains, for example. So this is the analysis. Okay, now we have the second quantity D. So let's see how to evaluate D. So when to evaluate D in the frequency domain, we first use the differentiation property that we've discussed before. So let's call the function gt, which is a differential of xt, and we know that the Fourier pair it means multiplication of signal in the transform domain. It's the multiplication with j omega. Okay. Similarly, for example, if you have the differential in the frequency domain, then the Fourier dual will be the multiplication of jt with signal xt in the time domain. So those are Fourier duals. Okay. For now, since we are considering the differential of xt, it is simply j omega x j omega, which we are going to denote by g of j omega. And we also note that, so if you recall, what we said before was that if you have to evaluate x j omega, and you have to do that at t equal to 0, it means that this t has to be replaced by 0, so this is 1. It becomes xt dt simply. Okay. Have we done this? No. I think we have made a mistake. It has to be the other way around. I mean, we have to consider the Fourier inverse relationship. So this has to be xt. So xt would be the Fourier synthesis equation. It will be 1 over 2 pi minus infinity to plus infinity. It goes the other way around. So this is xj omega. So if you are evaluating xt, synthesizing xt from xj omega, then you can do this. I mean, you can replace t by 0. T, since the integral is over omega, so if you have to do this for 0, so x of, what is x of 0? I mean, you can see this x of 0 for yourself. This becomes equal to 1 over 2 pi x of j omega. Integration, same limits. Okay, let's not put them again. X j omega, and then the exponential 0 is 1. So just forget about this term, and you're left with d omega. That's it. This is your x0, and this is precisely what it is. So d is g of 0, 1 over 2 pi g of j omega d omega. Okay, so this is the I mean, this is the signal at time t equal to 0, the value of the signal at time t equal to 0 in terms of the Fourier transform. So we conclude that g of j omega is j omega x j omega, so you can plug this over here. Okay, and if you do the integration, you have to probably have to do this by integration by parts, and considering the simple relationship of x j omega for part a and b, the first part will evaluate to 0 in figure 414a. So for this part, the differential d by dt xt is 0 at t equal to 0, and the second is minus 1 over 2 under root pi. Okay, so that's the value of the differential at t equal to 0 for figure 418b. Okay, so you see we have used the differentiation properties and the Parseval relation to evaluate the quantities E and D. They have first energy, second is the differential quantity, and we have not evaluated the inverse Fourier transform. We don't know what signal xt is. We don't need to know. Why? Because we know there are relationships that I mean, given the Fourier properties, the relationship that exists that can ease our analysis. If you have to evaluate the energy or the differential, you can use the properties, and it makes your analysis much simpler. Okay, that's the idea. Okay.